Alright, so I'm going to start the recording. Let's go ahead and get to work. Can you guys see the polar coordinates page, hopefully? I can put up the feed on my phone so I can see what you're seeing. Because I didn't hit the right thing. Okay. There we go. Gotta go down that labyrinth to get it up there. So, I've already drawn the points on here, but let's still go over them. So, as I was telling you last time, polar coordinates are defined by an r and a theta. This mouse is going nuts. Let me stop using that today. And we can define points by many different values of r and theta. So the first exercise down here was just to plot these points on the polar plane. So the first one is radius of 2 and an angle of pi over 6. So radius of 2 puts us on this circle right here. And then the angle says pi over 6, which is right here. So that's why my dot is there for A. The second one says now a radius of 3, but an angle of negative 2 pi over 3. So a way you can do that is you can say, okay, what is 2 pi minus 2 pi over 3? Well, that's 4 pi over 3. So starting at 0, I can go around to the angle 4 pi over 3. Now, first off, radius of 3 means we are somewhere along this circle. And then angle of 4 pi over 3. So I go around, I see 2 pi over 3. There's 4 pi over 3. So if it's an angle of 4 pi over 3, and that radius right there is B. Okay. Then the third one, again, says radius of negative 2. Well, that still means a radius of 2. So I'm still in this circle, right? Because I can't have a negative radius. It just means that once I find the position, then I need to flip 180 degrees. Because remember, I gave you the thing that said r and theta is equal to minus r theta plus or minus pi. So if you go 180 degrees away from that position, that's effectively the same thing as a negative radius. So for C, we've got to find the angle 7 pi over 6. That occurs right here. So a positive radius of 2 would put us here, but it asks for a negative radius, so we have to go the other direction, which would then be 180 degrees from that, which is pi over 6. And that's the same dot as A then. I don't understand this tablet sometimes. Okay. Doing okay so far? I can't watch the screen and see the chat, unfortunately. So you say how much of this stuff's going to be in the final? I'm not sure. Maybe one or two problems. And this is the unit circle including 15 degrees. Not sure what you mean by that. Alright, let's find D. So radius of 1, that puts us on this here. And then negative 8 pi over 3. So again, and this time we've got to do 4 pi minus that. Because 2 pi is only 6 pi over 3, right? So it's not big enough. We'd still have a negative angle. If we want a positive angle, we have to do even integer multiples of pi. So 2 pi, 4 pi, 6 pi, and so on. So that's going to give us 4 pi over 3 again, which is right here. But we have a negative radius, which means... Wait, did I do that right? 12... Yeah, it should be 4 pi. Okay, and then negative radius. So it should be right here is where I should have had it. Right, and the last one, E, is a radius of 4, so that puts us on this circle. And negative 17 pi over 12. So I did the math up here. That's 7 pi over 12. So find that on your axis here. Let's see, I see 7 pi over 12 right there, which means if the radius was positive, we'd put our point there, but because it's negative, we have to go to the opposite side. And there's E. Okay. So when I was saying that we could represent points with different values, right, notice A and C are the same thing. But there's other ways I could do it, right? I could say, let's see, I could do 2 and 13 pi over 6, and that would still be the same point. So there's many different ways to give the same point. So that's an exercise in how we can plot them. But now we want to know how can we change from one coordinate system to another. So before I continue, is everyone okay with if I just write on the sheet as opposed to working on the board today? Okay. So As I said, this next part is converting from one to the other. So this asks us to convert to polar or Cartesian. So if we start with a Cartesian, we have to convert to polar, and that set of equations is given right here. So if I've given an x and a y, I can find an r and a theta. So r here is the square root of x squared plus y squared. So that's square root of 1 plus 3, or square root of 4, which is 2. Then the angle is arctan of square root of 3 over 1. So what is the arctan of the square root of 3? Anybody know? Nobody sure? All right. It's pi over 3 for that angle. So my coordinate system would be 2 and pi over 3. Second one wants us again to convert from Cartesian to polar. So r equals square root negative 2 root 3 squared plus a negative 6 squared. So this is going to be 4 times 3 in the first one here, or 12. The second one's going to be 36. And let's see, is there a perfect square in there? That is 4 square root of 3. And then our angle is going to be negative 6 over 2 root 3. Or the arctan of negative root 3. So that should be negative pi over 6, or a positive 11 pi over 6, right? Right, so then, yeah, I missed my negative there. So it'd be positive, sorry about that. So just pi over 6 again. So let's see if this makes sense. Cartesian point is 1 square root of 3. So x is 1. Square root of 3 is almost 2, right? So it'd be a point like right here in the Cartesian plane. In the polar plane, we would have to measure the angle. So does this angle look like pi over 3? Wait, why did I put pi over 6? I'm losing it. It's 60 degrees, not pi over 6. It's the same angle as before. So, does it appear that that is a 60-degree angle and a length of 2? Well, yeah, I believe that. So the point I'm trying to make there is that if you overlay the Cartesian and the polar planes, they should overlap the points that you find. So for instance, this one right here, it says negative 2 root 3 and negative 6. So negative, negative would put me down in this quadrant. So x would be somewhere out here. X is negative, or y is negative 6. So it'd be somewhere down there. So then the angle we're looking for is this. The angle that the problem is going to give us is only going to be this angle. Right, because whenever we do the arctan, it's going to give us the value in, or the value of the angle closest to the x-axis. So I have to do a couple things here to my answer, right? Because 4 root 3 and pi over 3 puts me right here. So instead, I either need to make my radius negative, or I need to change my angle to, let's see, what would that angle be? Add pi to it. So 4 pi over 3. Does this make sense to everybody or no? All right, anybody else want to give some feedback? So no, it does not matter if you change the radius or the angle, just as long as you've picked one that represents the point in the correct coordinate or quadrant. Yep. I think drawing is the most effective way. I don't know if there's necessarily another way. I guess you could convert it back and see if it gives you the same thing. That's another way you could technically do it. But I think it's pretty easy to figure out what quadrant it's in, and then from there, make sure that both the polar and Cartesian coordinates work. So this next one, or these next two, are going to require the other set of equations, the x equal r cosine and y equal r sine. So x equals 2 cosine 2 pi over 3, and y equals 2 sine 2 pi over 3. So this is 2 times negative 1/2, or negative 1, and this one is 2 times square root of 3 over 2. So you just get square root 3 out of that. So yeah, Tom, you're just making sure that the 2 points correspond to the same exact point in both the Cartesian and the polar plane. And by that I mean if you were to overlap the 2 planes, there'd be a single dot. Otherwise, you haven't actually converted from one plane to the other, right? You've made some new point. So this is saying my radius is negative 1 square root of 3 for the, I'm sorry, that's my Cartesian. So if I plot the Cartesian, x is 1, negative 1, and it's up root 3, so somewhere around here. So this angle should be 60, and therefore that should be 120. So 2 pi over 3 times 180 over pi. That's 120, so that's good. That's the correct angle. And then it says a positive radius of 2, so in the same direction as the angle. So that's good. The point and the point in both, so Cartesian and polar, correspond to that point. Yep, that one is good. All right, let's try this one. So x equals r cosine of 3 pi, y equals 4 sine 3 pi. So cosine of 3 pi is going to be negative 1, and sine of 3 pi is going to be 0. So that tells me I should be right here. So again, angle of 3 pi, you'd go 1, 2, that's 3 pi, and a radius of 4. So again, that one looks good. So we've plotted polar coordinates, we've then converted Cartesian and polar coordinates into one another. The next thing that we would like to do is convert a polar equation to a Cartesian equation. And those require those same relationships from above. Everyone okay for me to go ahead and start this part? Okay. So hopefully that other stuff made sense since I asked you to at least try to look at it before. Maybe that hopefully solidified it for you. So converting equations. R equals 5. This one's lovely. All right, we've already got a relationship that says up here for x and y, and we've also got this one, right? So out of those three things, what do we think r equals 5 is going to give us? So I'm thinking that we use the r squared equation here. And if r is 5, well then r squared is 25, and that equals x squared plus y squared. That, my friends, is the equation of a circle with radius 5. And that should make perfect sense to you because polar equations and polar coordinates, right, is a set of concentric circles, and all we were told was a radius of 5. So in the polar plane, that's a circle with a radius of 5, and it's the same thing in the Cartesian plane. It's just in the Cartesian plane, we represent that by x squared plus y squared equals 25, and in the polar plane, we can just write r equals 5. The second one has r times cosine. Well, above we have an equation that says x equals r cosine theta. So I can do a direct substitution here, and I get x equal 1. Well, that's just a line. Right? X equal 1. So those two things right there tell you a lot about polar coordinates, right? The first problem, r equal 5, that's a really simple equation in polar. Not so bad in Cartesian. We're used to Cartesian, but x squared plus y squared equals 25 is a little complicated. The next one, x equal 1, super easy in Cartesian. Convert it to polar, it's now r cosine theta equals 1. So representing circles in polar, very easy. Representing lines, a little strange. So now we've got to start figuring out what these complex equations are. So first off, as we saw up here, these equations are represented by r equals, typically. So anytime you see a function of theta, they really just mean r. Okay, so r, I guess I should just say, is some function of theta. Just like y is a function of x. So the very first thing we should do here is say r equals this. Now the first thing that most people want to do here is say, okay, well, I've got a number times sine and I've got a number times cosine. Well, we've got x equals r cosine and we've got y equals r sine. So why can't we just replace those two things there with x and y? Well, the problem with that is that those values for r would be different. And that can't be the same, right? Or can't be the case. So yeah, you're right, Abood. So I'm going to do x divided by r is equal to cosine, and y divided by r is equal to sine. And then I'm going to substitute those in. So I now have r equals 1 over 4 times y over r minus 3 times x over r. And now it's just a matter of doing some algebra. So I'm going to factor out the r's. So I have 1 over r out here times 4y minus 3x. And dividing by r is like multiplying by r in the numerator. And so if I divided both sides by r, it would disappear. And then finally I'm going to swap this with that 1. And then even beyond that, I'm going to solve this for y. So guess what? That there is also the equation of a line. One with a slope of 3/4 and a intercept of 1/4. Did I do that too quickly, or are you guys okay? Alright, well, if you have a question, let me know. This one here, again, there are different values for what we might want to be r. So, of course, we change the q of theta to r. And I'm going to replace cosine with this and sine with that. Then I'm going to multiply the r, or I guess multiply through by r everywhere. And I'm sure you're sitting there going, well, that's great, but we've got x, y, and r now. However, we've got an equation for r squared. Right, r squared is also equal to x squared plus y squared. So now I've got this, but we're not done. I'm going to put all of this onto one side of the equation, and I'm going to leave a little space. Anybody have an idea why I left those spaces? So you're both almost right. I would like to complete the square. So yeah, good job, Ross. The reason I want to do this is I have no idea what this thing is right now, right? I want to know what this equation gives me. So I want to complete the square here. So I would take 8, divide by 2, and square it. So that's 16. But if I add 16 over there, I've also got to add 16 over here. And then the other one is going to be negative 2 divided by 2 squared. That's going to be 1. So then I need to add another one over here. So this all equals 17 on the other side. And the nice thing about completing the square is now I can factor each one of those. So this becomes x plus 4 squared plus y minus 1 squared equals 17. Do you recognize that equation? That's right, it's a circle. Let's see, I think this circle is shifted. I'm forgetting the shifts off the top of my head. I want to say it's shifted left 4 and up 1. And it's got a radius of the square root of 17, which is going to be approximately 4. So something like that. That looks pretty terrible, but you get the idea. Yeah, I'd have to check off the top of my head. I can't remember if it's, I think it's x minus h, x minus, or y minus k equals r squared for the formula, and the center is at hk. So I'll check that. And the important thing is you got a circle there, right? So this turned out to be a circle that's been shifted from the origin, or the pole. So I've got one more of these to do. And this one looks super complicated, but it's really not that bad. So I've got 1 equals, I'm going to leave r. Actually, I'm going to pair r and cosine together because x equals r cosine, right? So that's x, and then the cotangent. Cotan of theta is equal to cosine over the sine. And if we put in their counterparts, that would be x over r divided by y over r, or x over y. And then we've got 1 over r here, and cosecant is 1 over the sine. And sine is equal to y over r, so we really get r over y out of that. And that's good because that gets rid of all our r's for us. And if I factor out the y there, or the 1 over y, and then finally move it to the other side, I have a parabola. So look at how complicated a simple parabola shifted down by 1 unit looks in polar coordinates. Anybody need a minute after that? All right. So that's all of the section for polar, where we've plotted polar coordinates, we've converted them to Cartesian coordinates and vice versa. We've also converted polar equations. So inevitably we have to get to some kind of calculus with these things. And so the next thing we want to do is take derivatives. So here is this long drawn out equation. But in fact, it's not terrible because it's given to us. All we need is dr d theta and r, and then to plug it in. So, first off, what is r? Well, again, r is some function of theta. So, that is r. Okay, so r equals 3 sine. Dr d theta is the other thing we need to find. So dr d theta is 3 cosine theta. Part A says find the slope, it should say of the function, it just says of the at, I should say function here, at the given value. So dy dx, that's our slope. Dr d theta, sine theta is already there, plus, now plug in r. So basically everything I'm plugging in, I'm going to put parentheses around so you can see where it came from. And then on the denominator we have dr d theta times cosine minus r times sine. So I've got 3 cosine theta sine theta plus another one. So that's really 2 of them. Or 2 times, right? So that's 6 cosine theta sine thetas. Okay, there's 3 of them and then another 3, so that's 6. And on the bottom, I've got 3 cosine squared theta minus 3 sine squared theta. This is one of those times where that sheet with the trig identities really comes in handy. The sine of 2 theta is equal to 2 sine cosine. And cosine squared minus sine squared is equal to cosine 2 theta. So if I were to simplify this, right, I got 6 over 3 there. It reduces to 2. So then I have 2 cosine theta sine theta. That is exactly sine 2 theta. And cosine 2 theta is equal to everything down here. And I canceled out that 3, but I'd have to factor it out first to do that. So there we go. And then finally, sine over cosine is just equal to tangent. So that simplifies really nicely. Right, it looks super complicated and ugly, and then all of a sudden it's just tan of 2 theta. So that's the equation for the tangent, or the slope of the tangent line. And so we just need to plug in the angle given. And that looks like minus square root of 3. And then part B says horizontal tangents. So when does the tan of 2 theta, the slope, equal 0? When you say next one, do you mean the next problem or part B? That's up to you guys. I mean, you could certainly be working on it right now. So if you just solve that, you get all those angles. So this is one of those ones where you got to be careful, right? It says on the page here over the interval 0 to 2 pi, but because you're dividing by 2, you can go out a little further, right? Because once I finally divide by 2, I get 5 solutions that are less than 2 pi. But if I would have stopped this part at 2 pi, I would have had only the first 3 solutions. So it should be theta. That's between 0 and 2 pi, not the, whatever the angle was that you got out of this thing. So this is the last problem in this section. I think if you guys like, we could probably go ahead and finish up the other section. I believe it's only 2 things. Actually, we could start this. I don't know if we're going to get it done. These guys are kind of tricky, actually. This one's easy. The arc length, that'll take 5 seconds, but these are a little tougher. But we should certainly start them. So would you all like to try this one? Do you want me to give you a few minutes? Or if you like, I can work it at the same time while you're doing it, and then you can just look and see what your solution is. Or if you need, if you get stuck, you can look at mine. Alright, so I'm assuming you guys are working on the problem because I haven't heard from anyone. So I'll go ahead and work it while you're doing it, and if you need, you can look up. Tom, I was asking if you all would like to try this problem. Okay. So go ahead and work, and I'm gonna put my answer up here, and like I said, when you're ready, you can check it out. So would you guys like a few more minutes? Do you want me to go over it? When you say part B, do you mean the problem 2 or the second half where it asks you to find the horizontal parts? I'm assuming you guys had no problem doing the first half. Alright, so for the second one, you were asked for up here, wherever it was, find the horizontal tangents, which means when the derivative is 0. So I took my derivative, which was this form, and I actually converted back to this one. And the only way to make a fraction 0 is if the numerator is 0. So I started with the numerator, which is sine squared plus cosine theta minus cosine squared. And I took the sine squared and I said, well, that's the same thing as 1 minus cosine squared. Put the cosine squareds together and then multiplied through by a negative number, or negative 1. So you ended up with positive 2 cosine squared minus cosine minus 1 all equal to 0. So then I had to solve that equation. That's a quadratic. And I factored it. So I need two numbers that multiply to 2 times negative 1. So that's negative 2. And they have to add to negative 1. Well, those two numbers are clearly negative 2 and positive 1. So I replace the middle term there with those two. And then I grouped the first two and the last two and factored out the common parts. So the first two here have a 2 cosine in common. Taking that out, this is left. And that's great because that's exactly what's in this other one. That means I did it right. Right, if they have the same thing inside. I just have to realize there's a 1 outside here. So then when I write my two factors, it's 2 cosine theta plus 1 is one of them, the other being the cosine theta minus 1. And then each one of those you just got to set to 0, so those are pretty easy to solve, right? Cosine theta equal negative 1/2 and cosine theta equal 1. And then it's just a matter of looking on your unit circle. No problem. So you guys okay if I move on to the next topic and get that started today? That way that on Monday we'll finish up, and then anything that's left, anything that's left we'll finish, and then the rest of the time will be for review. Okay. Gotta love that little tunnel. Ooh, that was neat. There we go. All right. Last couple topics that we'll cover for the semester: areas and arc lengths in polar coordinates. So it doesn't translate as nicely as we'd like. Before, we used to just do the area under the curve, and it was easy. But this time, if we want to find the area for a polar region, we've got to have this 1/2 out in front for one thing, and it's actually equal to r squared times dr or d theta, depending on what r is a function of. So if you're given the function, you have d theta, and if you don't have the function in terms of theta, then you use r squared dr. So we're most likely going to use this one for all of them. So it says sketch the curves and the area, then compute the area. So as usual, I'm going to do this on Mathematica for you. But I would also like you to try it on your calculator, because eventually you're going to have to do this. So I'll show you how to do it there as well. So while that's loading up, first thing you guys are going to need to do is go to your mode, which we've done many times now, and go to the function one. So you'll see there's function, parametric, we've already used sequence, and guess what? POL stands for polar. So if you click that one, then we can graph a polar function. So when you go to y equals, you should see R1. Let's see if I can... So you should be seeing that. I'm going to type in the equation that was given there. Which was cosine 3 theta. And again, the theta is just the x key. I'm going to make my window standard as usual. Now if I do standard, you probably can't even really see that. You get that weird little thing. Okay, so that just means we need to zoom in, right? So we need to go to the window. Our x max and x min I'm going to change to 1 and -1. And same thing for the y. And then it says x SCL, that's x scale. I'm going to make that, I don't know, 0.2, let's say, for both x and y. And then I'm going to go back to the graph. And wow, now look what I see. Now here's one thing I don't like. The scale on here is not correct, because all three of those things should be the same size. What does zoom 0 do? Yeah, zoom fit should work. So it'll fit it to the screen. But again, we get something that doesn't look exactly symmetrical, right? So I'm going to do this on Mathematica for you. So I want to plot, let's see, it's I believe the command is polar plot. What was it? Cosine 3 theta? There we go. Now you can see how nice and symmetric that guy actually is. So pretty neat, I hope. So now what I want to do, my goal, right, the problem says compute the area of one leaf, or sometimes I'll refer that as a petal more often. So I want one petal. So what I'm going to do is I'm actually going to find the area between this point and then double it to get one petal. So the question is, what is this value of theta and what is that value of theta? Well, r here is 0. What value of r, or what value of theta gives us an r of 0? My original function was cosine 3 theta. So if I let theta equal 0, cosine of 0 is 1. So that's actually out here. And then what angle then is going to give me 0? I think it's going to be pi over 2. So let's go from 0 to pi over 2. Actually, I think it's going to be something different, but let's look. Okay, so pi over 2, I start here, and I go all the way around back to there. I just want to get to here. So yeah, pi over 6 because I'm multiplying it by 3, right? So now you see I get just that portion. So if I integrate from 0 to pi over 6, I'll pick up this piece. And if I multiply that by 2, that'll give me one petal. So just a quick sketch, looks like this. This is angle 0, and this is angle pi over 6. So we want the area, which in our case is going to be 2 times, because we're only doing half of a petal and we want one petal. Then the area equation is 1/2 the integral of f of theta, which is cosine 3 theta, squared d theta. Anybody remember how to integrate cosine squared? So yeah, we need an identity. And that identity is 1/2 1 plus cosine of 2 theta. Now theta in this case is already 3 theta, so it's really going to be 6 theta in here. Right, so that's the formula. Cosine squared is equal to 1 plus cosine 2 theta over 2. So if we use 1 minus sine squared, that's kind of the same problem as using cosine squared. We still have a squared trig function. So substituting the values in. This is 0, that's 0. Sine of pi also 0, so just pi over 6. And the final answer then is pi over 12. So if I asked you for the total area, you would just multiply my number that I have here by 3. So it would be pi over 4 for the entire thing. So this may seem like it's really far out there, but you know, if you take a step back for a second, the only differences are, and the hard part is the fact that we've got to figure out what our bounds are, and they're kind of screwy, right? You have to think about those in a very different way than how we have done in the past. Once you get the integral written out, then there's nothing new, right? This is all review, but the formula is a little different, and finding the bounds is by far the hardest part. So any questions about that one? Alright. Parthy with her magic notes over here saying she's good. So maybe let's do one more of these, and then we'll leave the rest for next time. let's see, do we want to do this one? Let's see what this looks like. So just, oh, I do recall, darn it, I didn't fix this one. Please change this to sine of 2 theta, because 2 sine theta, that's no fun. No calculus is needed to solve that. 2 sine theta is just a circle. So that is sine of 2 theta. And that's pretty interesting looking. And it says on the question sheet, area bounded in quadrant 1 and 4. Well, quadrant 1 and quadrant 4, that would just be 2 petals. And so if we find the area of 1 petal, we can just multiply by 2. So we just need to figure out, how do I get 1 petal? What angles will get me to 1 petal? So again, I need the radius to be 0 at 2 different angles. So radius of, or if angle of 0, right, sine of 0 would give us a radius of 0. So one of our starting points should be here for theta equals 0. And then the other angle is going to be, what, pi over 2. So normally we would plug in pi, but because it's 2 theta, we need pi over 2. And so you guys should see now on your screens that we get 1 petal if we go from 0 to pi over 2. And you should be able to replicate this on your calculator, so please practice that at least with one of these functions, because I am going to ask you to do one of these on your final, and so you've got to be able to plot it. So 0 to 2 pi are the bounds. So again, we need area equals, now it's 1/2 integral, and in this case from 0 to, to pi over 2, and the function is sine 2 theta, quantity squared. Now in our case it says bounded in quadrant 1 and 4, so we need again to do 2 times what we've done so that we can get both of those. So that would cancel with that right off the bat. And then we have to replace sine of 2 theta. So sine, sine squared. Sine squared of theta is 1 minus cosine 2 theta over 2. Therefore, sine squared of 2 theta would just be cosine 4 theta in here. So I would substitute that in. So I'll pull the 1/2 out front. And this will be 1 minus cosine 4 theta d theta. Integral of theta is, integral of d theta is theta. And integral of cosine is sine, but because that minus is there, it remains negative. And we get a 1/4 in front. So this is actually a pretty good review of doing trig integrals. So sine of 0 is 0. This is going to be sine of 2 pi. That's 0. And once again, we just get pi over 4. So those are somewhat difficult in that we have to find the bounds and then recall how to do our trig integrals. The next couple problems that I guess we'll go ahead and do next time, because we've only got about 10 minutes anyway, they're a little different. And let me just go ahead and plot one of them just so you can see why. Alright, so square root of that for r, and the other one I think was just r equal 2, right? Yeah, r equal 2. Okay. So again, pretty interesting shape. You may, or for any of you that took me for Calc 1, that equation there, that 8 square root of 8 cosine 2 theta in polar is the infinity sign. And I give that in Calc 1 in Cartesian coordinates. It's an ugly equation. It's like x squared plus y squared equals the quantity of x squared plus y squared squared, something like that. So anyhow, the problem here asks us for inside of this shape, which they call a lemon skate, or lemniscate. Never pronounced that properly. And outside of the circle. So if you look at the plot, outside the circle would be out here and inside the shape. So we're trying to get that and that. So we'll do that next time. The important thing is we've got to find this point and that point. So similar to what we did before, we have to set them equal and solve. So if you like, you can try that on your own. So we'll have that one, this one, and the arc length will take 5 minutes to do. Those problems are simple. Actually, if you like, we can go ahead and get those out of the way and then just leave the other two. So let's do that. Length of an arc is given by this equation. Compute the described arc length. Well, I have r, I just need dr d theta. So dr d theta is going to be 2 or minus 2 sine. So my arc length is an integral from 0 to 5 pi over 6 square root 2 cosine theta squared plus a negative 2 sine theta squared d theta. That's just 1. So you're left with the square root of 4, and that's 2. So you get 2 integral 0 to 5 pi over 6 d theta. And that's just 2 times theta, 0 to 5 pi over 6. Just that. Super easy. You're saying it's blurry? I don't know why the camera would get blurry, but let me see. The feed looks okay on here. Okay. So let me just do this last one, and I'll let you go. So I still need dr d theta. That's going to be 2 theta. Arc length is integral from 0 to pi, square root, r squared, which is going to be theta squared squared, plus dr d theta squared, so that's 2 theta quantity squared d theta. So take out a theta squared out of those two. It can come out of the radical as a theta. Dang it, I keep doing that. Do a u sub. So this is going to be 1/2 times 2, no, sorry, 2/3 u to the 3/2. Plug u back in. And plugging those in, we're going to have pi squared plus 2 to the 3/2 minus 2 to the 3/2. If I didn't do something silly there by going so quickly. So I know I did this really quick, but there is not a lot to those besides just plugging in and doing the integration we've been doing all semester. So any questions about the arc length or the plotting of polar functions, anything about polar coordinates really.